In this example, I want to look at integrating 2 tangent x times secant squared x with respect to x two different ways. The first way, I'm going to go ahead and use my u as the tangent of x. So if u is the tangent of x, du will be secant squared x dx. And when I solve for dx, I can divide both sides by secant squared, and I'll get du over secant squared of x. Okay? So let's go ahead and kind of put this together. So 2 times u times secant squared x, and my dx was du over secant squared x. So those cancel. And what I'm left with is the integral of 2u du, which is going to be u squared plus c. And of course my u was tangent, so we'll say tangent squared of x plus c. And that's the integral using u as the tangent of x. Let's go ahead and look at the same exact integral though, so let me copy it down. But instead of using the tangent as my u, let's go ahead and use secant as my u. Okay, so then du will equal secant x tangent x dx. And then dx will be my du over secant x tangent x. Okay, so let's work this problem. So 2 times tangent x, I'm going to break this secant squared up into a secant x times u. And then my dx was actually du over secant x tangent x, which tangent x's cancel, secant x's cancel. And I'm left with, interestingly enough, again, 2u du, which is u squared plus c. But this time my u was secant squared. So the same exact integral, but in one case I get tangent squared x plus c, and in the other case I get secant squared x plus c. Well, how can that be the case? The tangent squared and the secant squared are not the same things. Well, let's go ahead and differentiate both of those. So we're going to differentiate tangent squared x plus c, and we're going to differentiate secant squared x plus c. And I think we'll see some nice things. Both will have to use the chain rule. So let's go ahead and do this. So the 2 comes out front. So 2 times the tangent of x, and then times the derivative of tangent, which is secant squared. So 2 tangent secant squared. 2 tangent secant squared. Okay, well that seems legitimate. Same thing on this one. The 2 comes out front. So secant, and then multiplied by the derivative. So secant tangent. And we could rewrite this because I notice I have secant squared. So 2 secant squared times tangent. 2 secant squared times tangent. So a very interesting situation here where when I took my original integral, depending on how I went about doing it, what I used for my value of u, I got 2 seemingly different answers. But when I went ahead and went backwards and differentiated both of my answers, I actually got the initial expression once again. So despite the fact that tangent squared x and secant squared x are not the same functions, we had this plus c that kind of was unknown to us, because what's the relationship between tangent squared and secant squared? Well, you can start with the fact that sine squared x plus cosine squared x equals 1. And if I divide all of those terms by cosine squared x, I get one of our other known Pythagorean identities, tangent squared x plus 1 equals secant squared x. So while they aren't the exact same functions, how do they differ? Well, they differ by a constant. And what happens when you differentiate a constant? Well, it goes to 0. So that's why we were able to see that integrating this original expression seemingly ended up in two separate answers, tangent squared x plus c and secant squared x plus c. But the relationship between the two of those functions, tangent squared and secant squared, they're only different by a constant, so when I went ahead and differentiated both, I ended up with the same expression. And again, it's because that constant took the derivative of that and it went to 0. So, interesting approach to this problem.